Hi class. This video is about some basics of vectors, very important objects that we'll be using a lot in this course. For most of you this is review, but if you have any questions be sure to contact me. So a vector is a geometrical object that has both a direction and a magnitude or a length. And the magnitude in particular, or the length, must have units for anything that we're dealing with that are physical quantities. And there are many quantities in physics that are described by vectors, such as velocity. There are two basic operations for vectors that are crucial. One is addition and the other is scalar multiplication, and we'll go through these individually. Addition, if we have two vectors a and b, which geometrically, here's a, it's a direction and a magnitude. I've written it in the plane because that's the easiest way to draw it. And here's a vector b, also in the plane. I can define a vector a plus b by transporting b parallel to itself along a, and then going from the end, the beginning of a to the transported tip of b. The combination gives me the vector a plus b. And for a flat space like what we are dealing with here, a plus b is equal to b plus a. And so that means that vectors allow us to marry sort of these geometrical concepts of direction and position with algebraic concepts like addition and eventually scalar multiplication. One example of vector addition is the definition of relative velocity. Suppose we have a boat, here's my rendition of a boat, traveling on the water. There's a velocity of the boat relative to the water, that's some vector v. There's also the water itself may be moving with some current, that's the velocity of the water with respect to the land. And if we're here on the land, we actually would like to understand the velocity of the boat relative to the land. Vector addition gives us a very simple way to calculate the velocity of the boat relative to the land. It's just the sum of the velocity of the boat relative to the water plus the velocity of the water relative to the land. Now, along with this concept of addition, we can also define the concept of subtraction. In order to do so, we have to define an object, the zero vector. And this is a vector with no magnitude. Its magnitude is 0, and therefore its direction is arbitrary. The negative of any vector a is just a vector of the same magnitude but with the opposite direction. So if this is the vector a, negative a could be viewed like that. And if I follow my rules of how to add a and negative a, which is a minus a, we just get the vector 0, basically the vector that starts and ends at the same point. In addition to addition, vector addition, there's the concept of scalar multiplication. And here, if we start with a vector v and some number, lambda, this is a real number, it could be either positive or negative, then lambda times v is scalar multiplication. Lambda is referred to as a scalar, that is a number, a fancy way of referring to a number, and v is a vector. Lambda times v is a vector which has the same direction as v, that is at least for lambda greater than 0, but its length is expanded or contracted if lambda is less than 1 by an amount lambda. So 2 times v would be a vector in the same direction as v with twice the magnitude. 1/2 v would be a vector in the same direction as v with 1/2 the magnitude. Minus 1 times v, if lambda is less than 1, just changes the direction and then scales the length appropriately. So minus 1 times a is just minus a. Now, given any two vectors, w and v, we can v and w, we can actually consider any linear combination of v and w, av plus bw, for any numbers a and b. The set of all of these numbers, all of these vectors rather, av plus bw, is called the vector space spanned by v or w. Geometrically, this is a plane, a two-dimensional plane, spanned by v, w, and any combination of v and w. A related concept is if we have these two vectors v and w, they're said to be linearly dependent if and only if I can find numbers a and b such that av plus bw is equal to 0. If we think about this for a minute, what this says is that the vectors v and w are essentially in the same direction, and v and w can be expressed as multiples of one another. And in that case, the vector space spanned by v and w is, instead of being a plane, is just a line. the maximum number of linearly independent vectors in any given space that we're talking about. It's just the dimensionality of the vector space. We are largely going to be interested in 3 dimensions. So here is a 3-dimensional coordinate system, x, y, and z. This is a right-handed coordinate system, so positive x is in this direction, positive y in that direction, and positive z in that direction. And we usually take our basis vectors to be vectors of unit length that line up along the coordinate direction. So I hat is a unit vector in the x direction, positive x direction, j hat is a unit vector in the positive y direction, k hat is a unit vector in the positive z direction. We will normally be able to express, therefore, any vector, say velocity, in 3 dimensions in terms of some component vx times I plus vy times j plus vz times k. So again, this is a vector in the space spanned by I, j, and k. And these coefficients, whose linear combination with the basis vectors gives us the vector itself, are called the components. And components are extremely important because they allow us to reduce the geometrical operations of adding vectors and multiplying by scalars to real algebra on these components, vx, vy, and vz. So this is establishing a basis, and using these basis vectors allows us to start doing all the kinds of manipulations we can do on numbers, we do on the components of vectors, but they have the geometrical implications and interpretations that we'll be talking about. One last thing, these basis vectors I, j, and k, since they have unit magnitude, instead of an arrow, we'll often refer to them by putting a little hat over them. That just says they have unit magnitude. But since you will often see different kinds of notation for these vectors I, j, and k. You might see x hat, y hat, and z hat to refer to the unit vector in the x direction, y direction, and z direction. So again, in these columns, we're referring to the same basis vectors just by different names. Or if we want to emphasize that these are basis vectors, we'll sometimes use the notation ex, ey, and ez with the hat on them to show their unit vectors in the x, y, and z direction. Or to later when we're talking about curvilinear coordinates, we'll generalize this and we'll talk about e1, e2, and e3 representing the basis vectors along arbitrary 1, 2, and 3 coordinate directions. Finally, let me just review for you sort of examples in which we use vectors in physics. Some of them refer to a point particle that's moving. We can talk about its position. If we're talking about its position in flat space, which we will be dealing with in this class, then that position is actually a vector itself. If you have a curved space like the surface of the Earth, that's generally not the case. But even on the surface of the Earth or any curved surface, velocity, which has to do with changes in position over very small distances, is a vector always. Acceleration, changes in velocity, are a vector. Force, the force acting on a point particle, is a vector. And Newton's second law is an expression in the form F equals ma. This incorporates scalar multiplication here. M, mass, inertial mass, is a scalar. It has only a magnitude but no direction. Momentum, similarly, is m times v. It's scalar multiplication of velocity by mass. Now, in addition to the vectors referring to the properties of a point particle, we're also going to be interested in the concept of vector fields. Vector fields are a vector at every point in space and time. So, traditional examples of vector fields in physics that are important are the electric field. At every point in space and time, if we have a test charge, it will feel an electric field, and the force equal to its charge times the electric field. There can be as well a magnetic field at every point in space and time. There can be the gravitational field, the acceleration that a unit mass or a test mass will experience due to gravity. Or if we're talking about the motion of a fluid, we can talk about the velocity of any little element of fluid as a velocity vector field. So this concludes our review of the basics of vectors. We'll continue discussing vector properties both in the videos and in class.